There are many different ways to, I don't know, many. There are a few different ways to implement a stack. We're going to write some code together to implement a stack as a linked list. We're doing this because I feel we need a little bit more practice manipulating nodes in our own linked list. And so we're going to do that for the perspective of a stack. I do want to be upfront and say that usually we do not implement stacks as linked lists. We can more efficiently implement stacks using an array. That said, like we're going to practice with linked lists, and coming up next week, you will have the opportunity to implement a stack as inside of it having an array list, essentially an array. So we'll do that later, and I think that's a more common way to implement a stack. But we're going to focus on doing it as a linked list. Implementing a stack as a linked list is easier than implementing a full linked list like we did earlier. Because with a stack, we're just interested in being able to push and pop, and therefore that's there's less cases to cover because when we push an element onto our stack, we're going to create a new node and insert it at the beginning. This is basically the add first method that we had written previously. And when we pop an element off of a stack, we're going to be removing that first node and returning its data, which is essentially the remove first method that we implemented previously. So in a way, today is a little bit of like almost review as we work through this. So let's give it a shot. So here is our linked list stack class inside of our Chapter 16 class notes project. And we already have the comments written and the instance variable defined. As we did with the linked list, we're going to keep track of the reference to the first node in the linked list or in our stack. We'll call that instance variable first. Just like we did with the linked list, when we make a new linked list stack, there are no elements. So therefore, we assign I'm going to say this dot first. I like this. We're going to assign null to first, just to be extra clear. That's how we designate that it is an empty stack. So we're going to focus on the next few methods: adding an element to the top of the stack, removing an element from the top of a stack, checking whether the stack is empty. We could certainly implement the peek. We're just not going to worry about that today. Also already implemented for us here is this static inner class node, just like what we had in the linked list class. Two public instance variables, data, which will be a reference to the element of type object, because this will also not be a generic, and next, which will reference the next node in the linked list, the next node in our stack. So let's fill some of these in together. And as we do this, look for like, oh yeah, this is familiar. This is like what we wrote before. We're just implementing different methods because now it's a stack instead of a linked list. So the method to add an element to the top of the stack is the push method. So a little review there from chapter 15. Public void push. The user specifies a reference to the element to push onto the stack. It's been a couple of days, so remember we need to be very careful to keep the concept of a node, which is our internal data structure to build up our linked list, separate from that of the element, which is the data that the user actually cares about. Those are two different things. So like we see in the diagram here, if the user pushes an element onto the stack, we will need to make a new node. We're going to have to initialize data to the element that they specified. We're going to have to change some links here to insert this node at the beginning of the list. The new node's next needs to refer to the current node that first is referring to. Okay, so we need to set the new node's next and initialize that, and then we can change the stacks first to refer to this new node. So just like always, order matters a lot. All right, first things first though, let's make a new node. So I'll declare a local variable called new node and say new node. And then we need to initialize the instance variables of the new node. So data will be set equal to element. And next is going to be set to this dot first. And then and only then can we say this dot first equals new node. This type of code is very similar to the code you worked on Tuesday, right? Where you're manipulating nodes in the linked list by changing that next instance variable to refer to a different node as you move stuff around. So that's it for push. We don't have other cases we have to worry about because push always adds an element to the top of the stack, meaning it's the first node in the linked list. So second method, pop. Let's look at pop. So here's removing an element from our stack. This is a little bit more straightforward. We first refers to the node we want to remove, so we can use first to find that node's data. And then to get rid of it, we simply have to change first to refer to what was the first node's next node. And that's it. And we're good to go. So let's see what that looks like. So when we remove an element, that's called a pop. When we talk about stacks, it's going to return a reference to the element. Element, we'll create a local variable element. It's going to equal this dot first dot data. That's how we get a reference to the element. We then remove that node by saying this dot first equals this dot first dot next. I think these multiple levels of like indirection start to get complicated, and the picture again is really helpful. So definitely refer to the picture as you're trying to figure out how to change these links. And then we can just return the element. Do we have any special cases we have to handle with the pop method? Yeah, absolutely. So we should always be checking for those null pointer exceptions, right? So if here we're saying this dot first dot data, meaning if this dot first is null, we're going to get a null pointer exception. So we better check for that. If this dot empty, that's a method we're about to implement. But basically, if the stack is empty, we will throw our new no such element exception, just like we did in the linked list case. So we do have a special case to handle here. If you look at push, we're always concerned that like if the thing before the dot could potentially be null, we could have a null pointer exception. So we have new node.data and new node.next, but we know new node can't be null because we just made it here. We're not worried here about, and we know this can't be null because this refers to the object whose code is currently running. So that's why we don't need to worry about null pointer exceptions in push. But looking down here in pop, when we see something like this dot first dot data or this dot first dot next, now there's the potential for a null pointer exception if first has a null value. So, all right, let's implement this empty method since we're using it. Public Boolean empty. We will simply return this dot first equals null. If this dot first equals null, that means it's empty, so we want to return true. That is our entire implementation of a stack. And we left off the peek method, but that's okay. Using a linked list. So not a lot of code, but definitely some complexity. we're not going to take the, this chapter is all about implementing the data structures, not so much using them. So if you switch over to the stack demo class, you can see that our demo code is already included here. And so we can simply get rid of the comments and then actually run this demo code, which creates a new linked list stack, pushes 3 different elements, Tom, Diana, Harry, has that classic while loop that's popping off the element one at a time and printing it out as we go. So therefore, we should see Harry, Diana, Tom, because a stack is a first in, last out data structure. So if I hit run here, it runs it all. It prints Harry, Diana, Tom. It expected Harry, Diana, Tom. That's a great sign.